Okay, now we're on the last leg of chapter 18. We're going to look at the principles here of addition and subtraction of phasors. Key point says only phasors that lie along the same line can be added or subtracted directly in polar form. Phasors not on the same line must be added in rectangular form. So all that's telling you is that the two vectors on the x-axis here, a and b, can be subtracted from each other. A positive 7 minus a 5 units will leave a vector of 2 units. Okay, so that ends up being our resolved or resultant of those 2 units. And the same thing applies for the others. So the only time you can do this directly is if they lie on the same line. If we consider the phasors labeled Z1 and Z2 in the diagram, we have Z1 equal to 1 unit at 30 degrees. Actually, it's 1,000 k ohms. And Z2 is 1.5 k ohms at 50 degrees. So we've got these two vectors. And so if we wanted to add them together, the easiest way to do this is to convert them from polar to rectangular. So 1K at 30 degrees becomes 866 ohms plus J500, and 1.5 at 50 gives us 964 at J1150. Okay, so with those two, you can simply add the terms together, add the J terms together, add the real terms together, and you will end up with a total then of 1830 ohms plus J1650. So they just simply add then at that point. Converting them to polar, then 2.46 k ohms at an angle of 42 degrees. If we consider the phasors labeled Z1 and Z2 again, finding ZT, express the answer in polar form. Again, we do the same thing. Z1 and Z2 listed in polar form. We convert them to rectangular form, which gives us 1.73 k ohms plus J1 k ohms. The Z2, 1 k ohm plus J 1.73 k ohms. Again, we add the J terms, we add the real terms, and we end up with a polar sum of the two, 2.83 k ohms at minus 15 degrees. If we look at equivalent series circuits, the equivalent series circuit, they're using ESC as the abbreviation, of components in series is the resultant of the vector addition of the resistor, the capacitor, and the inductor. So if we have an example here, you can see R1, R2, and X sub L are all terms that can be added together. Again, you have to respect the real and the imaginary components. R1 and R2 then become 12 k ohms, the X sub L 15 k ohms. So we again put them together in a rectangular form, 12K plus J 15 k ohms. Converting that using the trigonometric functions, you get 19.2 at an angle of 51.3 k ohms. Okay, again, we do the same thing here. You can see we've got two resistors, we've got a capacitor, and an inductor. Each of the capacitors and the inductor have to be treated separately because they are a positive and a negative. So when we add R1 and R2 together, we get our 7.4, and then we add 12K, we subtract 3K. At that point, we can combine them, and we get 9 k ohms of imaginary. That should be imaginary right there, J. Okay, and that will give us then a polar form of 11.7 k ohms at an angle of 50.6. In dealing with equivalent circuits, we can also use our relationships for solving for X sub C or X sub L. And in doing so, with a given values, a frequency of 2.5 kilohertz, a capacitor of 10 nanofarads, an inductor at 600 millihenries, R1 and R2, they want us to find the equivalent. So at this point, we need to first find the ohmic value of the inductor, which gives us 9.42 k ohms, the ohmic value of the capacitor, which gives us 6.37 k ohms. Now at that point, we can combine all of the terms, R1, R2, X sub L, and X sub C, into our terms here. And again, that should have had a J there. And we will have a, in this case, they just wanted us to find the rectangular form. So that's our rectangular form. We can use the expression for finding X sub L, or using X sub L to find the value for the inductor, in this case in millihenries. So given in a problem where we have a 3.06 k ohm ohmic value for an inductor. I've got all kinds of mistakes here. Sorry about that. And we can find the equivalent inductance then, 2 pi times the frequency. Our frequency was given here in the diagram. F is equal to 2.5 kilohertz. And in doing so, we end up solving for the inductive value. Resonant frequency in RLC networks, or in LC networks, as we're going to find later as we start doing more along the lines of filters, we're going to deal with something called the resonant frequency. And so circuits that include capacitors and inductors where there is a frequency that the inductance, the reactive components for both the capacitor and the inductor equal each other, that is the magic frequency of resonance. So we label that F sub R as our resonant value, and it has a phase angle of 0. So the circuit is purely resistive at this point because the resultant reactance is 0 ohms. And so what really happens here is any energy in those two components is basically swapping back and forth at the resonant frequency. So we have these terms here, where X sub C equals X sub L at 0 phase angle. The impedance, R, is a minimum and I is a maximum. Okay, 1 over 2 pi FC is equal to 2 pi FL, and our resonant frequency becomes, when we solve this expression for L, for the resonant frequency, all we have left is 1 over 2 pi LC. So the voltage drop across the resistor must equal the applied voltage, and the voltage drops across each of the conductor and the capacitor and the inductor are the same. So we can end up then solving for the resonant frequency. And here we have an example problem where they ask us to find the voltage drops across each of the components, the reactance across the inductor and the capacitor, the total impedance, and the current, and draw the equivalent circuit. So you can see we've given the original circuit, and we're going to end up with this equivalent circuit where we just have a resistance because we are at resonance. So when we go through and solve for the resonant frequency, we get 2.25 kilohertz. Then we can use our expressions for capacitive inductance and inductive reactance and inductive capacitive reactance, and we get 3.54 K at that frequency. So this is the frequency where they basically nullify each other out. You'll notice that the values are the same. So X sub C and X sub L are equal to 3.54 K ohms at 2.25 kilohertz. So now we can gather our terms. The rectangular form then becomes 200 plus J 354 minus J 54. That's where they cancel out, and we end up with 200 ohms, which we could see over here in the diagram. The polar then relationship says that at 200 ohms there is no phase angle. And so at this point we can solve for the current, the applied voltage of 10 volt, and that impedance, which is purely resistive, gives us 50 milliamps. Then we can use Ohm's law to solve for the voltage drops. The voltage drops across the resistor, 10 volts. You'll notice here the voltage drop for the capacitor and the inductor. Since we have the same values, we end up with the same voltage drop. Now, this seems weird. You could look at this and say, how did I get 177 volts out of a 10 volt source? How did I manufacture almost 2 orders of magnitude? Well, we didn't. It's because of the energy swap here. So when added vectorially, these two values, in fact, result as 0. So the last step here, solving for the inductance, x sub L by 2 pi f, we end up with 47.4 millihenries. Okay, same thing here. You can go through and work this, solve for the values at the inductive and the capacitive reactances at the frequency given, 2.5. In this case, you'll notice that we are not at resonance, so we have 2 different values for our reactance. So when we put that in the equation for rectangular forms, we end up with a component on the imaginary axis, on the j-axis. So when we solve 200 ohms at J744 ohms, we get 770 at an angle of 75. Again, using Ohm's law, we can calculate for the current, 13 milliamps. Again, using Ohm's law to solve for the drops, the voltage drops across L and C. We notice we do not, since we're not at resonance, they're not the same value, so they become a difference here, 51 and 43, and we end up then with a voltage drop across the resistor, same current of 2.6 volts. Solving for the inductive value in henries, we end up with 47.4 millihenries. And one last example here. Again, we're looking at the same thing we saw in the last one. We're not at resonant frequency, so our reactances are not going to be identical, so that we end up with values that should be, I forgot all these J's. Values that are not going to nullify the reactance. Okay, so the rectangular form becomes 200 ohms at J840, and the polar then becomes 863 at an angle of 76.6 ohms. Solving for the current, we have 11.6 milliamps. Again, we can put it into Ohm's law, solve for each of the voltage drops, inductor, capacitor, and resistor, and we get our values for each of the drops. And now at this point, because we have a more capacitive circuit here, we're going to end up, because you can see the value up here, we got 3.98K, and we're going to subtract 3.14 from it. So we have a more capacitive circuit. This becomes our equivalent. The capacitor then is equal to 94.7 nanofarads.